Good morning, my dear young friends. Now, after teaching this chemical kinetics, now I am shifted to another important chapter of your course content. Of course, M.Sc first semester chemistry student, that is electrochemistry. It is a very big unit and you have to learn many important aspects of the electrochemistry. Now, one of the very important concept of modern electrochemistry is the Debye-Huckel theory. And of course, Debye-Huckel theory and its extension. Now, because you know that Debye-Huckel theory is based on many simple theories. And basically, before going into details of that Debye-Huckel theory, I am not saying that Debye-Huckel-Onsager equation, I am not saying the Debye-Huckel limiting law, I am just talking about the fundamental concept of Debye-Huckel theory. And it is basically based on the electrolyte solution and of course strong electrolytes. And of course there are so many limitations that it is applicable only for dilute strong electrolytes. Number one. Number two is that why I have chosen the title, I think I need at least 4 classes for complete Debye-Huckel equations. So today I will only discuss the overall concept of the whole Debye-Huckel theory. From the school level, I do believe that from school level you are studying the simple dissociation of electrolytes like acetic acid or sodium chloride or potassium chloride. So it is a school level teaching. But after listening this simple fundamental lecture, you will realize the importance of electrolyte solutions. And it has got tremendous applications in all the branches of science and technology. I am not talking about the chemistry. It is useful for physics as well as the material science as well as the biology. So you must understand that what is actually Debye-Huckel theory. Now you know that I always discuss about the national education policy, and that indicates the holistic and multidisciplinary concept, an integrated approach. Because when we derive that Debye-Huckel theory, you will find that it is one of the mathematical treatment. So it is the integration of, and most of the scientists, basically they are physicists. They are physicists. And you can call them the physical chemists. So in this short lecture, I will discuss some very brief history of that Debye-Huckel theory and the concept, actual meaning of the Debye-Huckel theory. Now, as you know that this is my style, that it is always I prefer and I refer some of the research papers. And now you really understand, because one of your friends, one of your colleague, class fellow, Mr. Girish Sahu, he has published a research paper in a very good journal of fluorescence. So that means you can understand the importance of the research papers. Undergraduate students are able to publish a paper. So it is a very important thing. So therefore, whenever I start any topic, so you know that there is a course outcome, then specific course outcome and the subject outcome, why we study that Debye theory. And fortunately, all these important books are available in our library. So you can visit any time to the library and you can go through all these very important books. So the number one book for the electrochemistry, I am talking about the whole semester first and semester second, because there are two volumes. One is Modern Electrochemistry by J.M. Bockris and a very well-known Indian electrochemist, A.K.N. Reddy, Amulya K.N. Reddy. So these two books are available in the library, and I always refer these two books. I like, and these two books are also available in our library. We purchased long back. One is D.R. Crow, very small book, but the concept is very simple, language is very simple. That is Principle and Application of Electrochemistry, D.R. Crow. And slightly modern type of things, Electrochemistry by Philip Rieger. And in addition to that, you can refer all the physical chemistry books. Like Levine, you will find the electrochemistry, or Atkins, Glaston. But basically, I will show you original research paper of the Debye Huckel and why I am just prefer, and I am asking my students that although it is a very old edition book, but when I gone through the original research paper of Debye and Huckel, I am talking about the 1923. Today is 2024. That means 100 century already passed. So 100 years ago, Debye and Huckel published this paper and developed this theory, Debye-Huckel theory, for of course strong electrolyte. So when I have gone through that paper, I have seen the derivations and other things, I found that most of the derivation written by the Debye-Huckel, and if you refer this book of the Glaston, so most of my derivation I have taken from that book, an introduction of the electrochemistry, and I think 5 or 6 copies are available in your library. So you can refer this book also. Although it is, let me confess, that is a very old edition. Now there are large number of research papers. I'll also discuss with you some of the things. And this book is also available. Also now Amazons or other, they are also selling this book, but it is the old edition. Again available in this or library, Electrolyte Solution, Robinson and Stokes. Very good book. It is available in our library. Now in addition to that, I have referred, because after 5 or 6 years, I am now teaching electrochemistry. Generally, I do teach thermodynamics or sometimes irreversible thermodynamics, but because the shortage of teacher, I am just teaching the electrochemistry. So I have referred some of the good research articles, and I will also suggest my student that you must refer this research paper, beautiful research paper, not research paper, because you know that in our country, Indian National Science Academy, you know that IISc Bangalore, you know, Indian Academy of Science, they actually publish a very good journal. The name of the journal is Resonance. Large number of important concepts of physics, chemistry, mathematics are involved in that journal. And it is a very old paper, published in December 2010, but it is a fantastic paper. And the title is, you see, that's very beautiful title, Peter Debye and Electrochemistry. And what is important, because you know that in our country, there are large number of scientific institutions, Department of Science and Technology or CSIR institution. Suppose you want to do some work regarding the medicinal plant. So you have to go to Lucknow, Central Drug Research Institute, like that. If you want to do some work on molecular biology, so CCMB. If you want to do some work in chemistry, so National Chemical Laboratory at Pune, where Dr. Indrapal did his PhD from NCL, like that. So similarly for electrochemical studies, there is an institute His name is Central Electrochemical Research Institute, Karaikudi, near Kharagpur. Karaikudi, I think. So one scientist from Karaikudi. And of course, in this article on the founding International Society of the J.M. Bockri's status of the electrochemistry and other things and things. And as I just told you a few minutes ago, that it is nothing, Debye-Huckel theory. It is only electric conductivity of the ionic solutions. That is the things. But you see that these electrolytic solutions or conduction is a paramount importance in science and technology. You will be surprised to know that this, now we are talking about this carbon capture and sequestering energy storage and other things, that is also based on the electrochemistry. If you are talking about the battery and energy storage, lithium ion batteries or sodium ion batteries, everything depends upon the ionization or dissociation or electrolytes and other things. So you can understand these things, and this is the original front page of that 2010. So this is a very simple article, and everything is given in this article. Secondly, now again you just close your eyes and think for the school days. You all know that in school levels you talk about the acetic acid ionization or dissociation. But do you know that the simple ionization or the dissociation, because whenever you are talking about the Debye-Huckel theory, it is directly related to the Arrhenius dissociation theory or Oswald dilution or Kohlraasch law. Because I am not saying that the Arrhenius theory is failed. I must tell there may be some doubts or demerits. And that Debye and Huckel, they modified the Kohlraasch law and other electrolyte dissociation and other things. And I am just showing you, you should be amazed and you will be surprised, excited that this is the original research paper, because Debye-Huckel theory is 1923 and Arrhenius ionization or dissociation, whatever it is 1889 or 1890, but he was awarded Nobel Prize on the simple dissociation of acetic acid electrolyte, and this is the original write-up of this Arrhenius. When a person got Nobel Prize, he or she has to deliver his Nobel lectures. So now you can understand the importance of that electrolyte solution or the conductivities of the electrolyte, because this is the Nobel lecture he has given in, because he was awarded Nobel Prize in 1903. And his whole research work is this dissociation or like that simple thing. Degree of dissociations, molar conductance, effect of dilutions. Okay, so so now you can understand what is the importance of the Debye-Huckel theory. And Debye is also a Nobel laureate. Debye is also a Nobel laureate. Onsager is also a Nobel laureate. So you can understand what is the importance of, just I derived the Debye-Huckel theory without giving the history. So I thought that at least in first lecture I should give the importance of the Debye-Huckel theory, and you will really understand that what is actually Debye-Huckel theory. So this is the original contribution of that great Arrhenius. And of course, when you read this paper, this lecture, you will understand this Arrhenius equation is also based on several contributions of other scientists, Bezeram and Sutherland, Kohlraasch, Oswald. I will coming all those things. This is the genesis of the Debye-Huckel theory. Okay, you follow my point? Now, after 100 years, actually his theory was in 1923. So there appear large number of research papers. And I will show some of the research papers which is published just November 2024. Why? Then you can understand the importance of the Debye-Huckel theory. But for the examination period, examination purpose, you just simply don't worry about the extension of the Debye-Huckel theory or the problems of the Debye-Huckel theory. determination of the activity coefficients and other things. You should only concentrate only on the simple Debye. I will explain these things. So see that the 100 years from the Debye-Huckel theory and beyond, it is published I think in 2023, because every time and they derives many things about these things. Similarly, this is also published in 202. So if you ask me, sir, what is the actual definition of Debye-Huckel theory? I'll tell you that it is nothing but the discussion of dissociation of the strong electrolytes, how they behave. Of course, we have to use thermodynamic model, activity coefficient like that. Then the inter-ionic attraction between the ions. And if you want to learn the electrostatic attraction between any ions, so you need the physics equation, the Poisson's-Boltzmann equation. And if you want to know the distribution of the ions, so again we need the statistical thermodynamics. So it is a combination of statistical thermodynamics, is the combination of that Poisson equations. Sometimes viscosity is also related. I will come all these points. So if you want, you can refer all such type of very important research papers. All the parameters can be discussed, I think. And then you can take your seat. So if required, so you just focus it like that. So the Debye-Huckel theory and its importance in model electrolyte solutions. Everywhere the things are same things. I am just a dialogue. The colleagues at the Technical University of Denmark has often stated life is too short for electrolytes, because they were strong electrolytes, so immediately it is dissociated. But if it is a weak electrolytes, so there is no complete dissociation. Just so another well-known scientist in the field of molecular simulation has recently said during the International Thermodynamic Conference, all my life I have tried to keep myself away from the water and the electrolytes. Like this type of, so you can understand the importance of this type of things. Now see, why it is so important, because whenever we are talking about this activity coefficient and any types of binary systems and other things, everybody, ionic liquids, whatever it is, the effect of solvents and other things. So everywhere we need that Debye-Huckel theory. So it is although it is also very recent paper and published in Journal of Physical Chemistry B, one of the best journal of physical chemistry. And again, if you see the title, New Electrical Conductivity Model, because after the discovery of the Debye-Huckel-Onsager equation, there are large number of different models. They slightly modified the Debye-Huckel theory. So you should not worry about all those modifications. You should concentrate only on Debye-Huckel theory and other things. Similarly, as I just told you a few minutes ago, because before coming to the class, every day I search the literature. What is the current trends of the subject, whether it is a kinetics or chain reactions or electrochemistry. It is my style of teaching, that is called the research oriented teaching. That is the difference between the school teaching, college teaching and the university teaching. And you are in the university teaching department, so you must know the current trends of that Debye-Huckel theory. And you see, today is 8th November, okay, and this paper is published in 7th November 2024. And everything is available in your smartphone and other things. So nothing new, nothing in that, but it is 2024 and modified Debye-Huckel-Onsager theory for electrical conductivity. Account of ionic charge, non-locality, etc. and etc. So that is not the important. Important point is that the still scientists are working on Debye-Huckel theory. So this is the brief history of that Debye. Now I am coming to the actual Debye-Huckel theory, and there should be no confusion. that there will be three types of question may be asked in the examination. One is generally normal Debye-Huckel theory, that is the starting point. Second is the Debye-Huckel limiting law, that is also related to Debye-Huckel theory. And third is the Debye-Huckel Onsager equation, which is called DHO. You follow my point? And but all are interrelated. All are interrelated. So this is the Peter Debye, and I have taken this photograph from some Wikipedia or some Nobel lectures and other things. Basically, he is a Dutch physicist. Again, I am talking that he is a physicist. He is a physicist. And he actually published the first paper. I'll show you the original research paper. It's a very big paper, and complete derivations is available in that paper. And just for a knowledge that he is a Nobel laureate, and he was awarded Nobel Prize, not for this Debye-Huckel theory, because you know that Debye is a very, very well known, that means his contribution is commendable in physics and chemistry. Actually, he was awarded Nobel Prize for the dipole moment and diffraction of the X-rays and Debye length. You know, there are lots of applications. And another scientist, of course, he is also physicist, but he is a German scientist. His name is Huckel or Huckel. So you all know that the Huckel's rules and other things, organic chemistry, that's other things. But here we will concentrate only on this Debye-Huckel theory, and this is the original research paper of this great Debye-Huckel equation. Of course, it is in the German language, and the journal Journal of Physical Just Christ, and you see this is 19, and you see 21 pages. You understand how big that paper is, and there are English translation is available, and it is available in the student. So I will request you to that through internet or your smartphone, if possible, just go through this whole English translation of this paper. Actually, because you know that I think you have already studied in B.Sc second year maybe, or in school level, that the colligative properties, depression in freezing point, elevation in boiling point, osmotic pressures, because he has taken large number of electrolytes and studied their freezing point depressions. You know, Hunter factors and other things, because you know that if it is a strong electrolyte, the Oswald dilution law maybe is not following. So how this colligative properties, it depends upon these things. So the English translation is also available, and this is actually Debye-Huckel equation. But what happened? There was another great scientist. His name is Lars Onsager, L. Onsager. When you promoted to fourth semester, there is a complete topic of the irreversible thermodynamics and Onsager reciprocity law, which is very important for examination as well as for irreversible thermodynamics and the biological system. So Onsager, when read this paper 1923, also he has published other paper also, then he was not convinced. I am not saying that Debye-Huckel equation, there may be some problems, but there may be some problems regarding the Brownian movements and other things, the mobility of the ions, speed of the ions. So this Onsager slightly modified that theory, and you can you can understand the tenacity of that great scientist. He was also Nobel laureate, but not for this Debye-Huckel-Onsager equation. He was awarded Nobel Prize for irreversible thermodynamics. So when he has some problems, and that time Debye was working in the Switzerland, a big university, ETH. So that great man went to ETH, met with Debye, and Debye was very happy. He accepted, and then he accepted his concern, and then of course in 1927 he published a paper. I'll show you that paper. So that is the ultimate theory. So of course, if you derive the Debye-Huckel-Onsager theory, it is the extension of Debye-Huckel theory. So first in my next class I will derive first the Debye-Huckel theory. Then I will derive Debye-Huckel-Onsager theory. Because you know that, suppose if I am talking about the electron, I will show you the diagram. If I am talking about the ions are just like a symmetrical. And suppose there is in center there is a positive ions, and this positive ions is surrounded by negative ions. Reverse case is also possible, that negative ions is surrounded by the positive ions. Basically ions are spherical. So we call it a symmetric system, or sometimes it is called the ionic cloud, or sometimes it is called the ionic atmosphere, like that. But suppose you just under the electrical field, there is a migration of that ions. Suppose there is the anode, there is a cathode, positive ions migrates one side. So there is a distortion of that symmetry. And of course, all the electrolytes are not soluble in water, so we have to use some solvent, and solvent plays a very important role. So that Debye-Huckel theory and Onsager modified these things. That what would be the effect if there is some electrical point. So sometimes it is called the asymmetric effect, then relaxation time, then suppose the solvent is also moving, so electrophoretic effect, then of course the viscosity plays a very important role. So when we derive the Debye-Huckel-Onsager, we will consider all those effects: electrophoretic effect, asymmetric effect, viscosity effects, and other things. And then of course we will derive the final equation of the Debye-Huckel-Onsager. Now we clear that there are two things different. Debye-Huckel limiting law is different. Debye-Huckel-Onsager theory also. So that is the contribution of that Onsager. And again, of course, this is in English language, because he published in Royal Society of the Chemistry. It's a very good journal. So single authorship. In this, if you see this paper, the first sentence, you see, this paper presents a modification of the Debye theory, the conductivity of the strong electrolytes. Of course, dilute solutions. As Debye has told you in this paper, the velocity of the ion is a conducting electrolyte, will be affected by the ionic atmosphere. And then of course he derived, suppose there is a solvent, and you all know, I'll show you I will not details discuss the Arrhenius equation or Ostwald dilution law or even Kohlraasch equation. But my intention is that this great equation is based on the main Arrhenius dissociation. And of course, the difference between the Arrhenius dissociation or Ostwald dilution and Kohlraasch law, there is a weak electrolyte, and that Debye is the strong electrolytes. And if there is a strong electrolyte, so naturally quite obvious is that there must be some inter-ionic attraction. That is called the electrostatic attractions. So only difference is these things. You follow this point? So this is the original research paper. report on a revision of the conductivity theory. The title is also like that, and it is in 1927, and Debye is 1923 after 4 years. And during this time, he has published large number of others papers also. You see, first paper based on the DHO report on a revision of the conductivity theory. Trans Faraday Society is a very good journal, Royal Society of the Chemistry. Second is also Onsager on the theory of electrolytes in 1927. Then again, Onsager and irreversible process in the electrolytes, of course, in 1932. But we are concerned only on this first paper. Okay. And similarly, when Debye has discussed with Onsager, so he also published a paper. He is also very good scientist, Halkenhagen, and it is not in your course. There is a effect of Halkenhagen and Debye equation. So I am not going into details of that theory. That is also one theory, effect of dielectric constants and other things. Now I am coming the last part of this the thing, that the development of this theory. And why I am just discussing these things, because now you remember that when you entered the physical chemistry practical, I had given you the one simple experiment. I think you don't understand that time the pK of acetic acid. pK of acetic acid, or you can call it a dissociation constant of acetic acid. What you have done, you have taken different solution of acetic acid, 0.1, 0.01, because that is the starting point of Debye-Huckel theory. And if you see when I was preparing this, I asked my student, Mr. Abhishek, I just prepare a PPT from the results of a student, because you have plot a graph between, I think, equivalent conductance under root of concentration, and you are getting such type of curve. That means when you dilute this acetic acid solution, the values of molar conductance or whatever it is, equivalent conductance, it is increasing. So why such type of things? And then you also calculate the degree of dissociation, which is very important, because there are two types of electrolytes: strong electrolytes, weak electrolytes, or intermediate type of things. It donates, yes, this is very school level things. It gives the ions, and that shows the conductance and other things. And while determining the pK or K of acetic acid, which is around 1.8 into 10 to the power minus 5, like that, 1.8 into 10 to the power minus 5. So if you perform the experiment carefully, so you see that your results are very similar, 1.8 into 10 to the power minus 5, like that. And you also observe the role of, I'll show you some of the results, and then you calculate this is most important, because this is the starting point of that, because when they have tried to calculate the degree of dissociation for weak electrolyte, so there is no problem. It is less than 1, very small value, and there is no deviations. And it depends the number of ions, because strong electrolyte, there is no complete dissociation. So if I take the acetic acid, this is 1.8 into 10 to the power minus 5, like that. And if you take the acetic acid, so weak electrolyte, so you can very easily calculate the K, the law of mass action. And then CS3. But if it is and basically this, you dilute it, so naturally number of ions will increase and the molar conductance naturally increases. But whereas if we Debye and Huckel, they have taken large number of acid, base and electrolytes, strong electrolytes. So they observed there is a deviation, non-linearity, and only number of ions is not responsible for the change in molar conductance. There may be role of the speed of the ions is also very important. Speed of the ions is also very important. So therefore they are trying to think that what should we do? Why such type of things has happened? And I'll show you the graph that in normal cases, if you take the acetic acid, such type of things have been happened. Suppose this molar conductance or equivalent conductance and under root of C or simple C, you can calculate the concentration. It is for the weak electrolyte like that, or maybe like that. But if it is a KCl or other things, then of course that is like that. There is no basic difference between these. Then of course this degree of dissociation is also very difficult to calculate these things, and it is not valid for the strong electrolyte. Then of course my second question, first I ask you to determine the dissociation constant, and it is also quite obvious, and it is developed in 1923, but before that there are so many theories, like Arnia's theory is Nobel Prize. Then Oswald is a great scientist, so Oswald dilution law you have already determined in your MSc classes. Actually this is alpha square, this is square 1 minus alpha V or C by V, like volume contains the number of gram equivalent or number of gram moles are like that. And naturally 1 minus alpha is almost, so I can write like that, K is equal to alpha square upon V, or alpha is equal to under root of K and V. So again this degree of dissociation is directly proportional to, it is suppose a constant in the volume and other things, or inversely proportional to the concentration. That is the Oswald dilution law. So again there is a problem that this Oswald dilution law is not valid for strong electrolyte. I am just talking about the genesis of Debye-Huckel theory. And if you read it, when you derive the Debye-Huckel theory, if you understand the Kallol's law, which is very, very important, which is again slight modification of this Oswald dilution law, you see that if I consider it is a molar conductance of a particular dilution and molar conductance of infinite dilution, okay, from extrapolated graph we can calculate that molar conductance of the infinite dilution. And if you plot a graph between the molar conductance and under root of C, a straight line, such type of things is observed. Or sometimes there is that in Kallol's law that ionic conductance of anion plus ionic conductance of cation, that is a different thing. So it is a simply straight line equation. But again there is a deviation, non-ideality behavior. And if you remember the Debye-Huckel, just after 5 minutes I will show you the Debye-Huckel equation. So it is just exactly similar to that equation, just where there in place of K there is two constant, A plus B. I will just example. So that means what I mean to say that Debye-Huckel equation or Debye-Huckel theory is based on all these theories, Kallol's or Oswald, and in addition to that there are other scientists also, like one J.C. Ghosh also published a paper related to the ionizations of weak electrolytes and other things. So that is the starting point of the Debye-Huckel theory. You got this point? This is so simple. So if I summarize these fundamental concepts of our old theory, so this is the first attempt. This is the means Debye-Huckel theory is the first attempt of non-ideality of electrolyte solutions. Why there is a change in molar conductance with the dilutions? What about the concept of degree of dissociation for the strong electrolytes? So therefore he has attempted these things, and the equivalent conductance is a function of the number of ions for weak electrolytes. But for strong electrolytes, it also depends upon the speed of the ion. Speed of the ion. And there is there is a relationship also. Mobility of the ions is very important for the strong electrolytes. And Kohlraasch experimentally established a square root of concentration decrease in equivalent conductance, as I have already told you. Y is equal to mx plus c, equivalent conductance. So such type of things. So again, definition, different types of definition. You can explain many types. That means first this non-ideality behavior, or you can understand that this migration of the ions or whatever it is, of course if there is some solvent. So Debye-Huckel theory is the understanding of, because it is nothing, it is a transport. B is converted into two ions, A plus B. So it is a one type of transport. So it is transport properties of electrolyte solutions. Transport properties of, now I am coming to the mathematics part. Now it is transport properties of electrolyte solution. And there are many transport properties, but here two important properties. One is conductance, another is the viscosity. So these are I am taking from your, now you just remember, if you just go to your lab and just show your practical records. And I always told you that, because this time I was busy with some administrative work, so I have not shown you the research results of that Glaston. But if you read it or if you can write, you can compare with your record also. That means you have already determined the 0.1, 0.01, 0.001, like that, 0.0001 m acetic acid. You have already calculated the equivalent conductance or molar conductance for acetic acid, no problem, at room temperature 27 degree or 25 degree centigrade. You see, I am taking this value from this book, Glaston. Don't worry about the ohms, because this is a very old edition. Now you use the Siemens S. So you see that there is a large difference. Means you see the higher side, it is very high, this side, and continue decrease. So you see 131 around 5.2, like that. So there is a clear cut distinction if you dilute these things. So conductance increases, molar conductance. Whereas if you take the potassium chloride or any types of the things, you see so that is the $1 million question and the starting point of Debye-Huckel theory. See, 0.1 is 128 ohms inverse 1 centimeter and 0.005 is 147. That means the range is 147 or 128, 146, 141. So there is no difference. So therefore they thought that why this thing is happening. Okay. So I should not say that it is a failure of Arrhenius equation, but I must say it is a defects of Arrhenius theory. That means no law of mass action is not valid here, because here is a 100% dissociation. And naturally, if we dilute the solutions, because it is a strong electrolyte, so there must be an interaction. So therefore Coulomb's law of attraction is also considered here. So there is a electrostatic attraction, or sometimes this is called the ion-ion interaction. Now if we are talking about the ion-ion interaction, so suppose there is a different types of ion is here, different types of ion is here, and it is spherical in nature. Ions are spherical in nature, and so the question of statistical thermodynamics, probability of, now the mathematics comes here, because, and if I apply some electrical charge here, so there may be some asymmetry effect, like that. It is negative this type. So, and definitely that ions carry some charges, and definitely there is a production of electrical potential. In case of Arrhenius equation or Oswald dilution, no concept of electrical potential, no concept of charge density. Now I am asking the student, suppose you are Debye, okay, and I am Arrhenius. I have studied the simple acetic acid, and results is there. This is my results, and I am unable to explain these things. Strong electrolytes, I am okay. I know the yes, there must be a electrostatic interaction. Coulomb's law is effect Q1. You all know Coulomb's law. Q1 is charge Q1 into Q divided by R. Distance is maybe distance other things. So can you tell me the how electrical potential is related to charge density? Just so, and the who will tell me? Batao. Who will tell the what is the relationship between, because now it is clear that our electrical interionic attraction is there, ion-ion attraction, electrostatic attraction, and you know the electrophoretic effect. But what is the question? That how do we study the change in electrical potential and the charge density? Anybody? Have you gone through this Debye-Huckel theory before coming to this class? No, you have not. No. So, okay. So that then we have to take the help of physics, because it is a, you do not know. There may be large number of positive charge surrounded by negative charge. There may be negative ion surrounded by positive. So it is a probability. As I always told that there are 60 students and number of students having number greater than threshold energy, like that, same thing. Number of students getting more than 80% marks. So we need statistical thermodynamics, Maxwell-Boltzmann distribution. And second is that the relationship between electric potential and charge density, we need the Poisson equation, Poisson-Boltzmann equations. And that you all know that Laplacian operator and like that, psi is equal to there is a equation, other thing. So if you understand, so therefore it is sometimes it is called the mathematical derivation of other things. So strong ion-ion interaction and solution show deviation from ideal behavior. The answer is that Arrhenius equation Sir, there is no, why we are not getting the linearity? Because there is a ion-ion interactions. Second, therefore, in order to understand this ion-ion interaction, in order to understand this ion-ion interaction or electrostatic attraction, a new theory is required. Therefore, and that is the behavior of that strong electrolytes. Of course, limitation is that the solution must be very, very dilute, but that is different thing. So therefore, Debye and Huckel developed this theory. So the electrostatic interaction between the ions is the key point. So it is in this method the thermodynamic properties like activity coefficient, because whenever you are talking about this positive charge and suppose there is a unit, volume unit, it's a mathematics derivation, Cartesian coordinate or polar coordinate, we just considered it may be x direction, y direction and z direction, but again it is a spherical coordinate. It is a spherical, ions are spherical, so Cartesian coordinate we converted into polar coordinates by r, theta and other things. So again it is a mathematics. So therefore I have to consider these things and other things, that how it is calculated and other things. Now if we are talking about the, suppose there is a positive charge, so if we are talking about the activity and activity coefficient, then electrical potential and other things, the question regarding the energy. If we are talking about the energy, then we have to think about the work and other things. So ultimately, if you want to calculate the number of or the actual energy or actual work done to bring a charge from infinite to these things, so then means automatically thermodynamics comes into the picture. So therefore, there is a relationship between the activity coefficient and the valency and charge size are also plays a very important role. So the Debye theory deals with the electrostatic potential, and according to this theory, ions in a solution primarily through the electrostatic forces. And of course, we have already during the chemical kinetics, we have gone through this ionic strength. So not only it depends upon the concentration of the solution, speed of the ions, in addition to that, it also depends upon the valency of course, when we derive the Debye theory, we will assume that is a univalent electrolyte. Because when we derive anything, so it should be simple system, Z plus, Z minus system. But it also depends upon the dielectric constant. D is very important. You will see that the value of the D, ionic strength. Because as ionic strength increases, but suppose therefore it is colligative properties, the role of solute, you know, role of solute and other things. So if the ionic strength is increases, that means if you take the more concentrated solution, the interaction become more pronounced and leading to the decrease of the activity. Naturally, there may be some more electrostatic attraction. So it will hinder the movement of the ions. Naturally, if there is electrostatic attraction, but whereas in the weak electrolyte, there is no such type of things. So ion can be freely moved. But and if solvent is there, so naturally solvent plays its own role, so viscosity and other things. So lastly, it is a mathematical treatment of ion-ion interactions. It is a mathematical treatment of the ion-ion interaction using the, I will explain, those who are mathematics students, they can understand the second order differential equation is also will be used here, and Poisson equation, if you just search from your literature that what is Poisson equation and why it is called the Poisson-Boltzmann equation and why it is called the linearized Poisson's equation. But if you are a biologist, if you don't understand, you simply write that it is a relationship between the charge density and the electrical potential, because that ions carry some charge and other things. That's all. And then of course, if it can be converted into the for spherical coordinate. Okay. So first I must say it is a mathematical treatment of the ion interaction. Second point, it is the first quantitative treatment, not qualitative treatment. Arrhenius equation, there is a qualitative treatment, but it is a quantitative treatment. because each and every parameters we have to calculate the activity coefficient and other things. Improvement over Arrhenius theory of electrical conducting in electrolyte solutions. So that is the use. I have already used 21 page the original research papers, and you can understand that, sir, from school level we are again you are talking about the Arrhenius and ionization, dissociation, but you see the importance, the contribution from, of course, 1903. I always give the history, or even 1890 to 1923, and in between there are a large number of scientists after the discovery of this Nobel Prize of 1903. There are excellent research papers published in Journal of American Chemical Society, the great journal, #1 journal, in, of course, 1924. The interionic attraction theory of ionized solution, critical presentation, Noyes, another great scientist. Then again, Chemical Reviews, 1933, Scatcherd, great scientist, coming age of the interionic attraction. So it's a simple thing, but Arrhenius could not explain these things, but they. Then again, Miller is a great scientist, the varial of a mixture of the ions, 1912. And of course, in addition to that, Bezerum, just like you have already studied the salt effect, Bezerum-Berum equation, Bronston-Berum equation, okay. Then William Sutherland, then as I told you, another scientist, the J.C. Ghosh. So, what I mean to tell you that it is not so simple. There are a large number of paper, and on the basis of their observation, on the basis of their results, ultimately Debye Huckel proposed this theory. And I think this is the last transparency. Actually, today's lecture is only introduction. So when I will derive the Debye Huckel, I will again use these same photographs, photographs, and my student Mr. Abhishek has prepared these things. So you can understand the things, and suppose this is A. And this is just because whenever we use the mathematics, so we have to consider it is not possible that we take a solution. So we have to consider a particular volume element and what is happened in that particular volume element. So in some books it is called the ionic cloud. Some books it is called the ionic atmosphere. And thickness of ionic atmosphere is very, very important. If you see old question paper, the last year or before last year, you will find large number of multiple choice questions based on this thickness of the ionic atmosphere. I'll explain that what is thickness of the ionic atmosphere, how it depends upon the dielectric constant, how it depends upon the valency, how it depends upon the temperature. If I take the water, you all know that the value of Q during that time. So I'll explain all these things. But if it is a weak electrolyte, so naturally the number of ions in the unit volume is relatively small. But now I will show you the original picture. He has prepared this picture. Yes, this is I have taken from a research paper, and Mr. Abhishek has prepared these things. Actually, this is the actual position. It is not like that only a ions are sphere. So in one case, so that is, therefore we need we have to consider positive ion as well as the negative ion. We have to consider the electrical potential for positive ion or for valency, then epsilon and psi, everything for one for plus, one for minus. Then, so why I am talking about the Boltzmann distribution? Because without this, I can't exponentially, you all know these things, no? Boltzmann distribution and other things. So without that Boltzmann distribution, we can't solve these things. Because I cannot say that maybe this positive ion is surrounded by large number of negative ions. There is a possibility of negative ions surrounded by positive ions, and there is some scattered of the ions. So until I use the Maxwell-Boltzmann distribution of ions, how do I calculate that distribution of ions in the ionic atmosphere or the ionic cloud? I have to calculate using Maxwell-Boltzmann distribution statistics and Poisson equation. Then of course I will get the final equation. So these three methods we will use. First, linearize the Poisson-Boltzmann equation for a simple electrolyte model. Then Boltzmann distribution law of statistical mechanics. So you can understand how difficult this thing. And then counting the electrostatic force in the thermodynamic model. But the limitation is it is only valid for the dilute solution. Now you can, I think, after this 1 hour lecture, you can understand the difference between Debye-Huckel concept, Debye-Huckel-Onsager equation and Debye-Huckel limiting law. Today I will not going to derive this thing, but I will just write the equations. So first is that, first we will derive Debye-Huckel theory of interionic attraction. I will get this thing. See here you see that this is the electrical potential. With respect to this distance, the distance is very important. Suppose if I am talking about these things, this distance, then the charge, and this here is E, here is the dielectric constant. I can use the D also. In some books it is written. I'll explain this thing. It is thickness of the ionic atmosphere and other things. And it is very simple. Why thermodynamic derivation, energy and free energy? You all know these things. The activity coefficient, because while deriving the, just you remember that primary salt effect. We use the Debye-Huckel limiting law. Log of activity coefficient is equal to minus Q 0.501 like that. Z plus J under root of mu ionic strength. So it is called the Debye-Huckel limiting law. There is a possibility of various numerical problem based on that Debye-Huckel limiting. How to calculate the activity and activity coefficient. You must learn. And third, now you just compare with that Kallol's law. Just you compare the Kallol's law. Minus A under root of C. So it is Debye-Huckel-Onsager theory. DHO. That is same thing. Suppose this is a constant. A and B is a constant. Don't worry about this. D is the dielectric constant. D is the dielectric constant. Eta is the viscosity. I told you na, transport properties. Means conductance as well as the viscosity is also important. Frictional things and other things. So you see lambda B, just like Kallol's theory, equivalent conductance, normal concentration, equivalent conductance of infinite dilution minus A lambda B plus B. So these are the constants. Just like, or a K, or you can write in some book it is write the capital K. But the same thing under root of C, under root of C. So it is called the Debye-Huckel-Onsager law. Clear or not? Today I have not derived any equation. It is a conceptual perspective. That means three equations are different. Your examiner is very genuine, so he will ask only one. But your examiner is very strict, so he will derive the Debye-Huckel-Onsager law. So now you can understand the difference between your undergraduate and postgraduates and school. So in PG level, if you directly write this thing, no, nobody will give you the number. You have to derive everything. Poisson-Boltzmann equation, Maxwell-Boltzmann statistics, and then you will get this equation first. And then from that, apply the thermodynamics, chemical potential, free energy, thermodynamic model, then the question of activity coefficient, and then of course, and sometimes what happens, you directly from this to this is possible, at least. So I will derive three equations in my next class. It is clear? In the meantime, I will request that you must, before coming to my class, at least you must go through your Indian books or whatever you want, like, just so that you can very easily understand this Debye-Huckel theory of interionic. It is completely based on mathematical treatment applying two concepts, Boltzmann concept and the Poisson-Boltzmann equation. And For Debye Huckel Onsager theory, we have to consider the electrophoretic effect, then the viscosity effects and other things. Thank you very much.